start my recording. Great. Okay. Feels like forever since I saw you guys. I guess it's just been a few days, but still. All right. Labs start this week. All right, so make sure you go to your labs. I know Paul went rogue. Is anyone in Paul's lab? I don't think so. Yeah. He started last week, I guess, with his Monday one. Then I told him to cut it out. We don't do that. We don't have labs in the first week. So I had to straighten him out. So he'll redo the same lab this week. Okay. So labs start this week. If you're in my lab section, or even if you're not, you're welcome to come to any of my lab sections. I actually had one just now from 1 to 2, so if that one works better, then you can come join me for that one. So the labs, I really just want you to use the lab time as kind of asking questions, right? So, oh, I tried this, it didn't work, right? I'll let your lab instructor kind of set you up that way. But if there are lab questions that you have, I did make the labs, so I'm the one who made the labs, and Paul and Sean are just kind of running through it for the first time. So if you do have lab questions, you're more than welcome to just come talk to me about them. There are little typos and just kind of typesetting things in there that you can ignore, but overall, all the material's there. Okay. And they should post the lab videos, which yours truly has made. So they're long, so buckle up, but all the material again is there. So make sure you go to your labs and get a feel for it, and go from there. Okay. Anything else I wanted to tell you guys? Probably not. Let's just do a little bit of review. Since it's been a while, okay. We talked about, where did we end here? That is the question. Okay. Here. So in terms of review, we talked about data collection, right? So how do we collect data? How do we get good data, right? And so we talked about data collection. Can you guys see the screen okay, or do we need to set the mood a little bit? Turn the lights out. I think we're okay. I think it was just that first day where we had sun, and now there's no sun, so yeah. So we talked about data collection. So we talked about the importance of having randomly selected data, right? Because we have to have a random selection in order for our sample to be representative of the population, right? So it is important that our data is randomly selected so that it is representative of the population. If we're reporting on survey data, right, we also talked about how important it is to report the response rate, right? So for survey data, we have to talk about the response rate, because a low response rate means that we have less reliable results, right? So the conclusions that we're drawing are maybe a little bit less reliable than we had hoped, right? So if reporting on survey data on survey data, we must report the response rate as a low response rate, oops, as a low response rate makes our conclusions less reliable. Makes our conclusions less reliable. So I guess I've got a bullet here, a bullet here. Then we talked about just bad sampling, things to avoid, right? Especially if we're doing surveys, right? We want to make sure that the wording is kind of neutral, and we want to look at, you know, non-response. How do we get people to respond to our survey? How do we avoid bias, right? So bad sampling introduces bias. Bad sampling introduces bias, right? So, and we talked about all the ways that we could introduce bias, where bias, remember, is just when we're systematically favoring an outcome, right? Whereas the definition of a randomly selected sample is where everyone in the population has the same probability of being selected into the sample, right? Whereas bias is when we're systematically favoring one outcome, right? So bias is systematically favoring a specific outcome. We talked about two methods of data collection, right? So mostly we focused on just observational studies, right? So we go out and we observe how many people visit our website, we observe their heights, we observe all these things, right? So we're not manipulating anything, we're just asking for information and we just observe it, right? The other option is to do an experiment. Now, obviously in business, we don't really do a ton of experiments, right? It's kind of hard to do because an experiment is when we're controlling all the factors, right, that are affecting a change in the response variable. And so we don't really have the opportunity to do that. And so we just touched on it briefly and kind of left it alone. But we did talk about the two methods of data collection. Right, the first one was the observational studies. Where we just observe information. And the second being experimental studies. And all I said was experimental design and experiments themselves are just a huge field of their own. So we're not going to get into them, right? But one takeaway message about experiments is that they're the only way that we would be able to say that a cause or a change in this causes a change in this, right? So an experiment is the only way that we can establish a causal relationship, right? For observational studies, right, we've just taken information, we've observed it, right, and we've said that a change in this, right, is related to a change in this, but we can't say that one causes a change in the other for observational studies, right? So experiments are the only way to establish a causal relationship. To establish a causal relationship between two variables, right? We're always talking about variables. So this causal relationship would be between two variables. Between two variables. Any questions so far? Good. All right. So I'd say that's the end of our review here, kind of a lengthy review, but there were a lot of topics that we kind of touched on, talked about, kind of parking lot them. They're not coming back, right? But they are things that I expect you to know. Okay. So I can't remember if we started 1.6 or if we didn't quite get there. Did we start it or no? Started? I'll pretend we didn't. So just, I guess it's still a review in theory. So 1.6, did I call it examining numerical data? So we want to know what our variables look like, right? So we've collected all this data, right? That's where we are. So now we have this pretend data set, and now what? Now we want to look at each of our variables and get a feel for what's going on, right? You didn't collect this data for just to have it, right? You're interested in knowing something about it, right? And so we'll start with data visualization, and then we'll move on to the summaries. Okay, but so we'll start with numerical data, and then we'll do the same thing for categorical data, but probably not until next day. Okay, so to visualize a numerical variable, just one numerical variable, we're going to use histograms. Okay. So to visualize numerical variables, we will use histograms. And to show you, I'll just steal this. Now you don't have to copy this out or anything. Obviously, it's just to have a little visual. I'll steal both of them. Yeah, they kind of toggled. Nice. So here we've got two histograms. Okay. And so a histogram, I really can't remember where we left off. Did we talk about histograms? No. Okay. Okay, great. Then I kind of do remember. So a histogram, right? Remember, we have a numerical variable, right? So we've got a column in our spreadsheet, and we've got a ton of numbers, you know, measurements, so speeds, heights, distances, all these measurements, right? And so they're on a continuous scale, right? And so to visualize these things, we are going to put them into bins, right? So each of these little sections is called a bin. And so here in the 10 to 15 bin, right, we've got not that many observations, maybe one or two. You can look here. So here's the 10-person mark, let's say, right? 10 data points, right? But let's say they're people, and I don't know, let's say we took a random sample of people, and some 10 to 15-year-olds snuck in. Happens, right? And so here we've only got a few, right? So how I imagine it is I've got these bins, and I imagine laundry bins or something like that, right? And I just say, okay, you go in here, you go in here, you go in here, and as you add people or manatees you want, or whatever you're counting, right? The pile gets higher and higher and higher, right? So each individual takes up some amount of space, right? And so that's where we get these bars from, right? And so we've got this kind of not very common bin of 10 to 15, and then slightly more common 15 to 20. So we don't. Whenever it goes to sleep, I remember that I have to change the settings, but I'll just try to keep it awake instead. Right, so slightly more common 15 to 20 bin, et cetera, right? The most common bin, 25 to 30. I'll show you in the lab how to change the bin widths, but usually R does a pretty good job of just figuring out an adequate bin width. And so it just defaults to some. But that's how histograms are made up. And so I'm not going to make you do a histogram by hand. I think that's insane. But I will make you generate one in the lab. So today we'll talk about kind of a poor man's histogram. It's called the stem and leaf plot, but we'll get there once we have some data. So the idea here is to look at the distribution of this data, right? So how is this distributed? What's going on here? Okay. So let's make a note of that. So we visualize data. We visualize data to see the distribution I guess, of the data. Kind of implied. So now you'll notice, right, that both of these have roughly the same shape, right? In fact, this shape is so common that it's called the normal distribution. Okay? So this kind of bell-shaped distribution we call the normal distribution. Okay? So one of the most common distributions is the normal distribution. And if we had a nice kind of smooth version of it, oh, that didn't turn out so nice, but it's the beginning of term. Had the break off drawing normal distributions, but don't worry, we'll draw lots of normal distributions, right? And so it's just got this bell-shaped distribution. So here we've got less common things, and then as we get closer to the center, right, we have the most common outcome, and then again, we've got less and less common outcomes. So here, right, imagine if you were looking at this, or no, let's say I call you, and I've made this histogram. Let's focus on that. We'll just start with this one. And so I'm on the phone, I've made this histogram, and I have to describe it to you. Right, so that's something that we have to do. You collected data, you visualized, you made this histogram, and now you need to describe what's going on. Right? In order to describe a distribution fully, you have to talk about three things. Okay? You have to talk about the shape, right? In general, what does it look like? The center, right? We're roughly, so give me an idea of where the center might be. Right? And of course, we'll develop calculations for the center, right? What's the actual center, that kind of thing. But for describing it, you're just look at it, get a rough idea of where the center is, and then finally the spread, right? So just the spread of these things. What are some reasonable values that you would expect to see in this data? Once you have that, right, then you'll be able to say, oh, that's a really extreme observation, right? So just looking at this one here, right, we've got this normal distribution. If I had to just quickly eyeball the center, I'd say around 25, just roughly, right? The idea being not nitpicky, you know, it's 20, it looks like 27 or something like that, right? It doesn't have to be like that. It's just to give me an idea of, is it in the thousands? Is it in the 20s? Right? Is it in the negatives? Right? So what's I'm talking too much, I guess, is what I'm gathering here, describing these distributions. So, right, just to give me an idea of what type of number are you expecting here, right? Something around 25, right? And the spread, anything between 10 and 40 seems to be pretty reasonable, right? So if I said, oh, I just found a new data point and it's 37, right? Just looking at this here, you would say, oh, that's kind of big, but okay, seems reasonable. And then, oh, I found another data point. Okay, what is it? It's -2. Okay, that doesn't really, right? That's a little bit outside here, right? So that would make -2 an extreme value for this distribution. Okay? Whereas if we look at this one here, now that we've honed our skills, right? Shape is the same, right? We've got this kind of approximately normal distribution. We'll talk about some other distributions, but we will only deal with the normal distribution. So we'll talk about some others, but in terms of the shapes, it's going to be normal. The center, I'm going to go ahead and say it's roughly the same, right? 20 to 40, 25's in there, right? So roughly the same shape and roughly the same center. The only thing that's different here is that the spread is between -40 and 80. 100 if you want to be nitpicky, but I don't want you to be nitpicky, right? The whole idea is just to get a quick sense of what's going on, right? Wiki wiki. So here, right, our data has bigger spread, right? So more variability in our data. So here, for this data set, if I said, oh, I found an observation that it's -2, you're just gonna say, oh, yeah, that's fine, right? Whereas here, an observation of -2 would be considered extreme, right? And so we need to know all three of these things, right? The shape, the center, and the spread to describe a distribution. So, yeah. Yes. We'll talk about how do we figure out if it's an outlier, but yeah, it would be considered an outlier, so just an extreme value. Okay. So to describe a distribution, we need to discuss three things. First one being shape. And I'm only going to give you two choices here. It's either going to be normal or non-normal. So anything that doesn't look normal, you would classify as non-normal. And I want you to be careful because we'll always be pushing for a normal distribution. So I want you to get in the mindset of saying, this is a normal distribution with the exception of this extreme value, or with the exception of maybe this high point, right? Because all the tools that we're about to develop assume that we have a normal distribution. So if we don't, we're kind of hooped, right? We don't know how to deal with anything but a normal distribution. And so, but luckily, it's a really common distribution. And so we're just going to deal with normal, normal versus non-normal. But just remember, you are always pushing for a normal distribution unless it's clearly not normal. For the center, just give me a rough approximation or even a range of values for the center, right? And the center would be wherever your imaginary kind of perfectly normal distribution, where would the peak be, right? Here is the center. So if you're looking at these distributions here, and if we just kind of put a blanket on here, smooth it all out, right? The center would be somewhere around here. Guess I kind of swerved off there. Doesn't matter. So the center, just give me a rough approximation. So you're just gonna eyeball it essentially, right? Just kind of quick and dirty, look at it, where's it centered, moving on. Right. Same thing for the spread. Another just rough approximation. So let's say this is histogram number 1 and this is histogram number 2. We've already talked about them. They have the same shape. They have approximately the same center, right? The only thing that differs is the spread. And so for histogram number 1 and histogram number 2, the shape is normal and normal. And if it makes you feel better, you can say approximately normal, right? If you don't like to say it's normal, you can say approximately normal. The center is around 25. Around 25. You could even say something between 20 and 40 for the second one if you wanted. There's the center. And then the spread, you would say it's somewhere between 10 and, is it 40? Yeah. Whereas for the second one, right, it's somewhere between -40 and 80. Right. I just use the numbers on the scale. Even if it goes a little bit beyond that, it doesn't really matter. Okay. So because the spread of histogram number 2 is much wider, right, we have a lot more variability in this distribution. So since the spread in histogram number 2 is much wider, I guess much wider than, oops, than histogram number 1, it has more variability in its data. More variability in its data. And this variability is something that we'll need to deal with in statistics, right? Because we know our sample, right? Every time that we take a new sample, it's going to vary from sample to sample, right? Our average is going to change a little bit depending on our sample that we've selected, right? And so we've got variability between our samples as well, right? So not just within our sample, but between samples. And so that kind of poses a problem when we're trying to say something about the whole population, right? Because it all depends on where our sample was, right? But luckily, the whole practice of statistics is trying to kind of harness that variability and figure out what's going on despite the variability. So that's where variability is important. Okay. Any questions about that? So on the assignment, or definitely on the test, I can't remember what the assignment looks like right now, but I'll give it to you next day. But I'll give you a histogram and I'll expect you to be able to describe this distribution. So you're going to touch on all three things, but just briefly, right? The shape, the center, and the spread. So some non-normal distributions before we move on. If we have something that looks like this, we've got this kind of bulb on the right-hand side, and then we've got this tail going to the left, right, or in the negative direction. So stats is funny because we only care about extreme values, right? We're trying to capture these extreme values and figure those out. So in this case, we're interested in the tail of things, right? Not the bulb where everything is going on, right? We want to know, okay, what's going on in the tail over there, right? And so this is skewed, which you've probably heard before, right? The data is skewed, okay? But I think in our minds, we would say it's skewed towards the right. But in fact, in statistics, we talk about the tail, right? So it's skewed in the direction of the tail. So this would actually be skewed to the left, right? Where are the extreme values? Okay. So this distribution is skewed to the left. Or if you want, you can call it a negative skew, right? It's moving in the negative direction. Either way is fine. same idea. If you have something like this, then you're skewed to the right. Or you have a positive skew. I'll say here, distributions are skewed in the direction of the tail. Distributions are skewed in the direction of the tails, or of the tail. This positive skew is kind of more common than the negative skew. If we're thinking about time, right? You can't have negative time. So often time will look something like this, right? Or money, right? There's a lot of money happening down here. That's pretty common. And then we've got these kind of extreme values, right? These outliers. And so it's skewed to the right. I can't think of any skewed to the left distributions off the top of my head, but money and time are pretty common skewed to the right distributions. So let's just talk quickly about the mode. The mode is technically the most frequently occurring data point, which doesn't really make sense for numerical data. And so the mode has kind of turned into a peak, right? So a mode is, I'll say a peak, because we could have multiple peaks. So a peak in the distribution So if we have something like this, right, where we have a mode here and we clearly have another mode here, right? So we have two peaks. We call this a bimodal distribution. That's only if you very clearly have two bumps. So if this were to happen to you, what's probably happened is that you put two groups together that should be analyzed separately, right? And so can't think about, I don't know, the heights of 1-year-olds and 3-year-olds. Right? 3-year-olds are just, they're all taller, right? Their heights follow a normal distribution in here, right? The heights of 1-year-olds follows a normal distribution, but when you put them together, right, you've got this bimodal distribution. So a lot of the time, if you have a bimodal distribution, it's really, the problem is that you put two groups together that should be analyzed separately. Okay. So if you have a bimodal distribution, or if you find a bimodal distribution, can't decide if it's 2 words or 1 word. I'll play around with it. Here I went 1 word. If you find a bimodal distribution, it is likely that 2 groups have been combined when they should be analyzed separately. So we're not going to deal with any bimodal distributions, but if they come your way, right, that's probably something that's happened. So then you might want to look at, okay, are you looking at, well, here at the college, maybe first years have been combined with third years, for example, something like that, where maybe you need to separate them up. I'll just emphasize it again, right? Unless it's very, very clearly not a normal distribution, I want you to push for a normal distribution, right? So you have to have something glaringly, obviously not normal to say that it's a non-normal distribution, right? So we will always be pushing for a normal distribution, right? So we will always be pushing for a normal distribution unless it is very obviously non-normal. So that's kind of the visualizing bit for numerical data. Right. Now, let's start developing some actual numerical measures of center and spread. Right. The shape is a shape. We can't calculate the shape. Right. We just look at it. Right. If something looks like a circle, you're going to call it a circle. If it looks like a bell curve, you're going to call it a normal distribution. Right. Same shape. So now, right, we've eyeballed the center, we've eyeballed the spread, but now we want some sort of, we want math and we want it now. So let's calculate, or let's look at what we use as the numerical measures of center and spread. One thing is that we've already talked about the mean and the standard deviation, right? The mean and the standard deviation are really only usable if we have a normal distribution. Right? So if we have a non-normal distribution, we should be using the median and the interquartile range instead. So those are four things that we're going to look at. How do we calculate these? How do we find these? Right? And we'll use a little example. So just make a little header here. So numerical measures of center and spread. So like I said, it's going to depend on if we have a normal distribution or a non-normal distribution. Okay. Or whatever I tell you to do. Find the mean, find the standard deviation, find the median, find the interquartile range. Okay. So depending on if we have a normal distribution, a normal or a non-normal distribution, our numerical measures of center and spread D. So we're going to talk about the normal distribution and a non-normal distribution. And we're going to talk about their center and spread. So like I said, for the normal distribution, the measure of center that we're going to use is the mean. Mean, we've already talked about it, right? That's the average. And for our spread, we're going to use our standard deviation. Standard deviation. I'll put little separators. For a non-normal distribution, we're going to use the median as the center and the interquartile range as our spread. Now, we haven't talked about these yet, and we probably won't until next day. So the interquartile range, which from now on, I'll just abbreviate IQR. The interquartile range. The thing with these is we can find and use the median and the interquartile range for any distribution, right? So it applies to both a normal distribution and a non-normal distribution. However, if we have a normal distribution, then the mean and the standard deviation lets us do so much more, right? So, but we should only use them if we have a normal distribution. And so, and the reason that I'm emphasizing that is because it's a really common mistake that people make, right? So think of house prices in Kelowna, right? And I'll even use it in examples, but what did we just say about money things, right? Money things, house prices in Kelowna, for example, tend to be skewed, right? So should we be talking about the mean? Probably not, right? We should be reporting on the median. So, but that happens a lot where we talk about the average even without discussing the distribution. And sometimes it's going to be on a skewed distribution, right? So that's why I point that out, because it happens quite a bit, right? That we use the mean and the standard deviation on something that doesn't follow a normal distribution. So we should be using the median and the interquartile range. Less powerful, right? We can do less with this, right? But more appropriate. So the median and interquartile range, just like I said, can be used for any distribution. So the median and interquartile range can be used for any distribution. But the mean and standard deviation are more powerful if we have a normal distribution. Are more powerful if we have a normal distribution. I meant to find a funner example, but I'll stick with this one because I'll steal it from the class this morning. But what I want to do is I want to show you how to find all 4 of these just by an example. All right, so I'll give you this example, and then we'll find the mean, we'll find the standard deviation, we'll find the median, we'll find the interquartile range given these numbers. Okay? So the example is, I'll try to find a better one later, but the distance flown in a day by 9 parrots. That's pretty fun. The distance flown in a day by 9 parrots is recorded below. In kilometers. So I'll steal it because then I can steal the numbers. Hey, it's a recap. Had to squeeze my 3.4 in there. Copy. So 2.8 kilometers, 1.3 kilometers, 0.5 kilometers, that's a lazy parrot. 4.7 kilometers, I made these up, obviously, so I have no idea if they're right or not. Should have made them about manatees. 3.5 kilometers, 7.1 kilometers. I don't know how far manatees swim. Maybe 7.1 kilometers. 1.9 kilometers, 2.1, and then I had to squeeze in my 3.4. I'll see if I can. Oh, I can. Space it out a bit. Okay. So it doesn't matter what the data is about, right? I'll give you a couple of numbers, right? Between 8 and 12 data points, I think is reasonable for working by hand. I'm actually pretty opposed to doing any calculations by hand, but we have to show you how to do it. I have to make you do it, so we're doing it. But I'm kind of the, I don't know. I think our phones can do all these calculations, so why wouldn't we just let them do it, right? But there's, I guess we like the discipline of making you guys calculate it by hand. We're stuck there. So you're stuck there with me. Anyways, it's pretty fun once you get the hang of it. So if I asked you to find the mean of these things, you already know how to do them, right? You would, right? If you had to find the average of these, what's the average distance flown? Then you would add these all up and divide them by 9, right? You already know how to do this, right? But here I'm going to introduce summation notation. Has anyone used summation notation before? Fun to say, fun to do. Sort of. I'm seeing some sigmas in here. Yeah. Okay, great. If not, we'll just go through it. Okay. So since this is an example, I'll do part A, find the mean distance flown in a day. Okay. Find the mean distance flown in a day. If X represents the distance flown, right? So here I'm just developing what we're about to talk about. So you don't have to do this every time, but let X be the distance flown. Right? Then remember that X bar, X with a bar over it, is the sample mean. Right? Anything with a bar over it is a sample mean of whatever's underneath. Right? So this is the mean distance flown for this sample. Right? So this is the sample mean of X. Right? And here, X is just representing our data. In terms of a formula for calculating the mean or calculating the average, we would write the sum, so a capital sigma of X over N. So it helps that we know how to calculate these things, right, when we put on summation notation. Fun to say, fun to do. Okay. So where the sigma of X, right, so the sum of X is read the sum of X, and it just says add up all your X values. So add up all your X values. So the sum of X, now I can't remember, I think is 27.3. Nice. Was it 27.3? Thanks. So if you add up all your X's, they add up to 27.3. Okay. And N is the sample size. Okay. And this one's going to be really important because it's going to come up throughout this whole term. I'm going to expect you to know what lowercase n is, and it's just the sample size. Okay. And N is the sample size. So here, N is 9, right? We had 9 parrots, 9 data points that we're looking at, right? So our sample size is 9. So if we had to find X bar is the sum of X over N, where the sum of X we just found was 27.3. Try to throw you for a loop. No such luck. I'll try again. Over 9. I want you to try to stack your equal signs, right? So whenever you can avoid it, try to avoid working across the page. Right? We're working in math. We should be stacking our equal signs and just showing the flow of our work downwards. Right? It gets confusing when you have to read across the page. So try to get in the habit of kind of stacking your equal signs. Obviously, if space is an issue, you can kind of loop around, snake around the page. Right? But try to stack them. Okay. So what is this little guy? I think 3.03 repeating. Just double check. 5 by 9. Phew. So the mean distance flown in a day is 3.03 kilometers. The mean distance flown in a day is 3.03 kilometers. as far as rounding goes, it's going to depend on the question. And if it's really unclear, I'll try to make a note, right? Round your answer to 2 decimal places, 3 decimal places. I would say shoot for 2 decimal places, right? But always keep all your decimal places in your calculations, right? And so if you're not too familiar with your calculator or whatever calculator you're using, there's usually a store button, right? Comes in handy. So you're going to store all of these values if they get out of hand. And then that way they'll just remember all your decimal places, right? And so try to keep all your decimals in your calculations. Then round to, let's say, 2 decimal places. Or as many specified in the question. A good rule of thumb is if I give you 4 decimal places, right? If I give you values to 4 decimal places, you should give me 4 decimal places back, right? If I give you 1, you can give me 1. If I give you 2, you should give me 2, that kind of thing. And so it just depends on the question. So try to keep all your decimals in your calculations because it will make a difference, right? And then at the very end, go to, I don't know, default 2 decimal places. Right? So we have found the mean, right? 3.03. And I know it seems like the work was the actual calculation. What people like/don't like about stats, depending on what you're here for, right? If you're here for math, I'm sorry, it's going to be half math, half interpretation. If you're here for the non-math part, congratulations, it's only half math. So it's going to be half math and half interpretation. Okay, so and that's what's different between stats and math. Math is just, you know, chug along, and then stats, you get a number, but that's not the whole deal, right? You have to interpret this number, you have to know what it means, you have to know what it's telling you, right? And so it's good to get in the habit, even though I won't necessarily be looking for a little concluding sentence, it's good to get in the habit of just kind of saying, here's the answer. The mean distance flown in a day is 3.03 kilometers. So, any questions about that? Oh, yeah. How about we find the standard deviation? Oh. So find the standard deviation of the distance flown. So remember, S is the sample, so lowercase s is the sample standard deviation. The formula for S is all under the square root. The sum of the x's squared minus n times x bar squared over n minus 1. Let me just, I know that's it, but it's going by memory. And I think, just to emphasize that this is one number, I'll put brackets around there. You don't have to have them on there. Okay. Here's what we're building up to. for our summation notation, right? Because here we've got summation notation again. One thing to notice, right, is here we want the sum of the x's squared, which is not the same as the sum of the x's squared. See, big difference. It actually is a big difference, right? So note, the sum of the x's squared is not the same as the sum of the x's squared. The sum of the x's squared, so the first one, hopefully you can hear it when I say it, so it's not all. The sum of the x's squared, the sum of the x's squared. Okay? We're not doing this. Here, we're going to have to first find the squared value of each of our x's, and then add all those up, right? That'll be the sum of the x's squared. So to find the sum of the x's squared, we need to first square each value of x. First square each value of x. Then add them all up, or then add them up. Before we do that, let's just talk about what else is going on in here, right? Because it looks like a big nasty formula, and of course this will be on your formula sheet, and there are other ways of setting up this formula. This is the one that I think is the simplest to deal with, right? And so that's the one that I have on there. They all will arrive at the same thing, obviously. Here's the hardest part, right? We're going to take each of our x's. I like to arrange them like this, right? So we have our data going across the page. Now I like to change it to move down the page. That's just because for me it's hard to read up and down, but one way or another, you're going to find the square of each x, right? And then you're going to add those up, and that'll take this spot here, right? That'll just be one value. We know n from before, right? 9. We know x bar from before, 3.03. Right? We can square that, that's fine. We can deal with that. And then we just have n again, which is 9 minus 1. So once we have this conquered, then it's all good from there. Right? And so we know n is 9, right? And x bar is 3.03 from part A. If you're using information from a previous part, you can just use the rounded version. Right? And one thing I want you to remember is when I'm marking more for process, right? It's way easier if you get the answer right? But if you have the right idea and you follow through, right? So maybe there's a little typo in there somewhere, right? And you just slip on your calculator or something silly like that, that's not going to bring you down, right? As long as you have the right idea, right? So let's say you found the wrong mean in part A, right? That would haunt you all the way through, right? But I'll just follow through with whatever you say is your mean, right? That's what I'll use, right? And if you did it right with your mean, then that's all I can ask for, right? And so I mark on process, takes a little bit long, It takes a lot longer actually, but it's what's important. Right? And so just follow through, just be consistent. Also, pro tip, if you're working through all these parts and there's one part that you can't find and another part hinges on it, just say, I can't find this, so I will use this as my answer. Right? I can't find the mean, so I'm going to use the mean as 4, and then just follow through. Right? So don't let those little hang-ups or hiccups rather get you down. Anyways, talk more about that closer to tests and stuff. Okay? So we know n, we know x bar, and so now I'll just see if I still have the data points. You probably have them on your page still, so, but for me it's hard to see. So here's my data points, and like I said, for me it's hard to read up and down, and so I just rewrite all these as x, and then beside it I'll write x squared, right? And so I'm just going to make a new column of all my x's squared. So I'll just write out 2.8, 1.3, 0.5, 4.7, 3.5, 7.1, 1.9, 2.1, and 3.4. I'll go back and steal it. I'm just stealing left, right, and center here. Hey, nice. So I've squared each of these values, and then I've added them all up. Right? Remember, if we put the summation down here at the bottom, the sum of x, right, was 27.3. And then we can make a note here that n is 9. Right. By copying and pasting, I saved quite a bit of work because it gets pretty tedious just squaring these values, right? But what you'll learn about me is I like tedious. It means that things are easy to do and I know what I'm doing. It's a nice feeling. So just plugging away, square it, add them up. It takes time, but it's not hard. So now we have the sum of our x's, we have the sum of our x's squared, we have our n, and we also know from before that x bar is 3.03. So now we can find s is the square root of the sum of our x's squared. I'll put that in brackets just to emphasize that it's one number. Minus n times x bar squared over n minus 1. So I have 114.11 minus 9 times 303 squared. So just the 303 is squared, right? Just as a note, over 9 minus 1. I'll do the 303 squared. I'll show all my steps just so you can kind of break it down. 114.11 minus 9 times 9.1809 over 8. Times that by 9. So we have 114.11 minus 82.6281 over 8. Square root of 31.4819 over 8 And do not forget that square root. Probably the most common thing that I see is you get to the very end and then you somehow forget the square root. So the square root of 3.9352375, and the square root of that is 1.983743305. Therefore, I'm assuming you guys are familiar with the therefore notation. Therefore, just 3 dots, the standard deviation is 1.98 kilometers per day. Oh. Any questions? See you guys on Wednesday. And if you have a lab, maybe even with me in a bit, see you then.